Discovery's 4 computers now have primary control of critical vehicle functions.
All right, everyone, welcome to today's ASRG webinar. But before we get started, I'd like to tell you a little bit about ASRG and get some of the legal stuff out of the way. ASRG is a nonprofit organization founded to support the development of the automotive security industry. We have developed a platform and a community to share knowledge, communicate through networks, and to build value with collaboration. This is a community for you, built by you, with the goal to protect our friends and family when using automotive products. If you want to learn more about ASRG or get more involved, please visit our website at www.asrg.io or send us an email at hello@asrg.io. Before we jump into the presentation today, let's get some of the legal stuff taken care of. The views and opinions expressed in this webinar are the views of those that have made them. They do not represent views or opinions of ASRG and are to be considered as informational. The use of this information is to be used by the individual and/or organization at their own risk.
Greetings everyone. I would like to extend a warm welcome and express my gratitude for your participation in today's webinar titled Guardians of the Code: Unleashing the Power of IDPS and TE in a Software-Defined Vehicles. My name is Gregor Knapik. I'm the solution architect for cybersecurity in VIC1, and I've been working since 2004 on cybersecurity. Started my diploma thesis in the car access group, working on encryption and secure data loggers, and moved on into a software integrator role and software engineering role. Spent also a couple of years in the semiconductor industry, worked on HSM, secure micros, secure elements, and other semiconductor components. And since 2022, I joined a company called VIC1, which is an expert in cybersecurity for IDPS, the VSOC, and the vulnerability management systems. And I have today with me Richard. Richard, can you introduce yourself, please?
Thank you, Gregor. My name's Richard Hayton. I'm the Chief Strategy and Innovation Officer at Trustonic, and I also chair the Trusted Environments and Services Committee at Global Platform. I've been in cybersecurity a long time. I did my PhD on distributed security over 30 years ago, and recently I've been working on embedded security with Trustonic. Good to meet you all.
So it can be seen that CVs related to automotive have begun to grow rapidly since 2019. Currently, these vulnerabilities mainly cause data theft or device hijack and other impacts, but it can be expected that in order to reduce these attack surfaces, the automotive industry will begin to face pressure to catch up on vulnerability patching, and the automotive industry's patching time has become shorter and the number of patches has increased, and there may be a situation where manpower technology cannot keep up. And when we look on the expanding attack landscape, attacks are no longer limited to APIs, but also begin to cover components on infrastructure. Judging from the attacks in the first half of 2023, we have observed that cars have been attacked more comprehensively, from cyberattack, kind of ransomware, to app, to CAN, etc. Now we look into future SDV environments, and these are the 3 categories with the main unseen risks. But why focus on these areas in particular? Because from the perspective of our security experts, this is currently the most likely place to become a breach. Standardization can promote an extensive cooperation in vehicle development, but it can also cause chain reactions, kind of supply chain attacks. APIs that are widely used are easy to connect and can provide services to customers, but they may also become target of hackers. And finally, in order to simplify the development simplification through centralized HPC, which is then fast, many applications can be run on it, but it may also be mistakenly thought to be safe, resulting in a single point of failure. Next, we will introduce those unseen risks. In order to achieve development simplification, SDV can run many applications on it through a centralized HPC. Therefore, it's not surprising that SDV will use isolation technology, like containers, virtual machines extensively. And therefore, the car factory feels that it is safe to isolate. But let's see what kind of unseen risks you can explore here. But this is actually a myth, because we have seen how container and virtual machines are being attacked in the IT world. Container virtual machines actually have many vulnerabilities. So when car manufacturers use this technology extensively in the future, such a scenario will happen to cars. It is scary, because the car becomes a centralized architecture, which can easily cause a single point of failure. And OEM and Tier 1s tend to use containers due to the cost and other benefits. However, the container escape issue, so-called privilege escalation, is a big concern. So an intrusion detection and prevention system, in short IDPS, is required more than ever before to help OEMs to fulfill R155 requirements for continuous monitoring and detection and provide a response. How to detect issues with your container technology? Behavior-based monitoring is required to detect and prevent privilege escalation. That's why we need to integrate a behavior monitoring module, which is part of an IDS, create CV-based rules and heuristic rules to detect the system behavior anomalies. For this, the relevant threat intelligence is required, and offer rules as a virtual patch to help the OEM and Tier 1 to mitigate the container escape issue, remove the roadblock in using containers. But let's look into another scenario. Imagine the car manufacturer would like to repair the car remotely or help you open the door remotely. Therefore, a VPN connection is being established between the service cloud and the vehicle. The problem is that VPN cannot prevent attacks to your devices. Hackers first break into the OEM's cloud. This is one way. Then they can use the VPN tunnel to get into your car. As a next step, they can use also credentials to operate the car. So for example, stealing the credential. In the future, they can log into the cloud and then use the cloud to control the car, such as the Sirius example shown. Or after a hacker approaches the car, use the mobile app and enter the stolen credential. You can use mobile apps to open cars, doors, etc. already today. But also, if there is a problem with the VPN software stack running in the car itself, the hacker can go in directly from here. And we have seen basically the real case scenario, how Fortinet warned of hackers targeting governments through VPN vulnerabilities. And we see these kind of issues steadily growing. To create virtual patches and expert rules for the IDPS to detect potential malicious behavior, organizations require the threat intelligence from various sources, such as Trend Micro, VIC1, the Zero Day Initiative, ASRG, and AutoISAC, among others. The vulnerability data comes from the software bill of material, which is updated periodically by the vulnerability management system, scanning the software binary images. And the process of creating rules and testing includes the threat vulnerability analysis, the rule creation, the hit rate and false positive testing, a performance and capability test to ensure minimum false positive rates and no impact on the target environment. And once the rule is qualified, it is optimized and a virtual patch file for the target ECU is created and stored in a database. Now, different vehicles might require different patches for various ECUs, since the different technologies are being used. Like we described, potential threats may come up from vulnerabilities in the VPN software stack. It can happen that the Docker engine has potential vulnerabilities, and privilege escalation is a threat. So verification is done before deployment to the vehicle. This can be done by the OEM, the supplier, depending on the communication patterns, and it can be deployed to the OEM vehicle fleet by VIC1 or the OEM directly. So in addition to being secure by design, like having authentication or access control, the IDPS with virtual patches and select access to expert rules can help you protect against threats from trusted credentials or exploits. For example, although it is legally certified, when it conducts suspicious activities, we will detect and block it. And thanks to the threat intelligence, our virtual patches and expert rules are always updated. Secure channel could be now enabled by VPN, HTTPS, and the public key infrastructure as an example.
You can think of your system like a city. It sits on top of some hardware and does a large number of very complicated things. And the IDPS system effectively acts as a policeman, watching what's going on and making sure that everything is as expected. But as with any defensive device, the IDPS itself can be attacked. If you can disable the defenses, it makes it easier to attack the rest of the city. And that's where Trustonic and VIC1 got together to look at how to protect this using trusted execution environment technology. So let me talk a little bit about that. A modern chipset, such as an ARM application class processor, has a security technology built into it at the hardware level called TrustZone. There are similar technologies in other chipsets. What this does is it builds a divide between the main part of the chip, the main operating system where hypervisors and everything else we've been talking about runs, and another area. This is the trust zone, an area which is more heavily protected and more highly isolated. What we do is we run a second operating system here, and you can think of this like a castle or a fort across the river protecting the city. Its job is to protect the main city, but it is just another operating system, but one built from the ground up with security in mind. There are very well-constrained ways in which the two cities communicate with each other, and this again makes it difficult for attackers. We call this a trusted execution environment. And when talking about TEs, the rest of the world is called the regular environment, the rich or regular execution environment. This is where your main operating system, hypervisors, containers, VPNs, IDPS, and everything else tends to run. And these things are around on all ARM chips for a very long time. You will find them in every cell phone, you will find them in every set-top box, you will find them in increasing numbers of controllers within vehicles. And the job of the trusted execution environment is to protect the REE assets. So for things like communication, it can manage crypto keys. For things like digital media playback, it is responsible for providing a secure video path to allow the video to be played back without anyone being able to pirate it. For things like device identity and secure boot, it's responsible for attestation, a way of proving secure manufacture, and also doing security audits and other low-level analysis of the device, far below what the operating system does, and therefore protected from anything the operating system could do, good or bad. It's also used at the application level, commonly for things like biometrics. If you have a phone and you unlock it with your fingerprint or your Face ID, that processing will happen within the trusted execution environment. It's also where user profiles can be stored to protect them, given that they are privacy sensitive information. And so things like payment applications, again, this is where the payment kernels typically run. Now the TE is a full operating system, but it is simpler. It is typically single vendor, and it's typically much more stable than something like Linux or Android. That means it's a great place to put security sensitive applications and operations. So when we talk about protecting IDPS, it's really against two primary attacks. An attacker may attempt to disable the IDPS system itself, because if they can knock out the security guard, it's much easier to then attack the system. And equally, an attacker may attempt to muffle its output. If the IDPS is generating logs of potentially nefarious information, setting the alarm off, if you will, the attacker may attempt to prevent that output from being recorded or from being sent to a server for analysis. These are two things that we could protect against. So to take the simplest first, file system-based attacks are relatively easy for an attacker because file systems are very common. So if the attacker can get a foothold in the system, they may try and modify configuration files. The TE can protect these files by storing them elsewhere. So the first thing we do is we store the IDPS policy within a secure file server which runs within the trusted execution environment. The IDPS fetches the policy from the TE when it needs it, and that avoids any attack in the normal operating system's file system from influencing the IDPS. Now we're storing the file elsewhere, we can also do things like validate that any updates are signed, and that signature verification happens within the TE, again making it hard for an attacker. The next thing we can do is that when the IDPS generates any sort of logs or other output, those can be stored directly within a log file or a database within the trusted execution environment. That allows us to store and analyze information in a privacy-centric way and away from the fingers of any attacker. We can also upload those logs securely if needed to an external server. Going deeper, we can do a lot more. So we can sign and encrypt logs. That's a relatively straightforward thing to do at a first stage. But we can also do things like attestation. So attestation is where we take keys injected during manufacture into the device, plus measurements made of the device. Things like what versions of software have been installed, whether secure boot has happened correctly, and other information similar to an IDPS, and including information from the IDPS itself. And that gives effectively a certificate that we can sign and send to a server to describe the state of the device, that can then be used by the IDPS to decide which rules, which configuration to send. There's lots more we've talked about doing, things like running parts of the IDPS inside the TE itself to do things like monitoring very early boot and give even stronger guarantees. The fact we can store logs entirely within the TE and have a full database within the TE means we can do many more things that would be not really possible in a regular operating system because an attacker could potentially modify them as you were trying to perform them. So we're going to show a little demo today. This demo is based on an environment using automotive grade Linux and a trusted execution environment, shown as the green and blue boxes on this slide. And what we have on the green side, on the regular side, is some Linux applications and an IDPS system from VIC1 running. And there's both user space and kernel space components to that. The IDPS here is effectively the policeman that an attacker may try and manipulate by changing the configuration logs. So what the IDPS is going to do is it's going to fetch the configuration logs from a trusted application running inside the TE, which in turn will store those configurations within the secure file system. I'm going to hand back to Gregor to go through the demo itself.
Thanks, Richard, for your introduction into the TE. Now let's have a look at the demo, how the IDPS can be enhanced using a TE. So let's have a demo where we start the IDPS system. On startup, the IDPS rules are loaded from the TE, Protected Secure File System, in short SFS, preventing attackers from manipulating them. In the next steps, the IDPS rules are set to allow the example web page to load, but to block any further malicious action. Once the attack is known, a new rule set can be deployed into SFS that entirely blocks the web page, and Xcarbon will be reconfigured with this new rule set called virtual patch. Now, if the same attack is mounted, the download is blocked as the IDPS rules were updated to block view of the suspicious page. Now let's have a look at the event log, which will show the vulnerability has been blocked. And as you can see, we detected basically a shell shock vulnerability exploit. So let's conclude the learnings from today's webinar. First of all, don't do it yourself security, because attacker technology is diverse and evolving rapidly, and you'll need a major layered approach to cybersecurity to protect your systems. Also, excessive use of technologies such as VPNs, TLS, code signatures all provide protection, but attackers will find and exploit weaknesses, and fixes take time. Therefore, IDPS is a vital tool acting as a guardian to protect these systems against any attack, and it's designed to be reactive and adaptive to handle new threats as they emerge. On the other hand, the TE is a major technology to store and process critical assets, and it can be used to strengthen systems by managing keys, configurations, and logs. And software-defined vehicles will require layers of defense that work with each other to maximize protection. And in this talk, we have demonstrated how a VPN, how IDPS and TE can work together in an SDV. We'd like to take a moment to express our gratitude to ACRG for making this webinar possible. And if you would like to stay connected with us, feel free to connect with us on LinkedIn or send us a message. Thanks, Richard, also for presenting together with me. It was a great pleasure. Thank you to the audience for your attention today, and have a great rest of the week. Stay safe and goodbye.